Hello. So I think let's get started. My name is Ashwin Raveendran. I'm a part of the eBay Cloud Engineering Group, and I'm here to talk about how we manage our Kubernetes clusters declaratively. So before we jump in, let's understand why eBay chose to use Kubernetes and what are some of the main reasons why we stand behind the Kubernetes as a cluster management solution. So first and foremost, we like the simplicity aspect of Kubernetes. There are a bunch of these primitives which Kubernetes brings in. The idea of the pods and replica sets. These are pretty awesome representations, the abstractions which a developer can easily understand. So think of these as patterns for distributed computing, which if more the people know, the more easier newer solutions can be built on top of these things. So that simplicity of understanding how your application is laid out is the number one thing which Kubernetes brings to the eBay ecosystem for us. The second part is flexibility. So while it is very simple, it also allows flexibility in that a developer can take his application runtime, decompose it into one or many units, and put it as part of a pod, and then you run these pods in a distributed manner. So though it is very simple, it's also extremely flexible. And obviously, something like Kubernetes is very efficient because it has a dynamic scheduler which powers how the workloads get provisioned onto these different nodes. And for operators like us who are operating these Kubernetes clusters at large scale, it is really, really flexible. So we have bent and adapted Kubernetes to match most of the operational challenges we have. And this talk, we will cover some of those challenges and how we have done that. And the last reason, and I think one of the foremost reasons, is the open source community. Kube has an extremely awesome community. We have had nothing but good things to say about them. So let's jump straight in to the declarative models, what we are basing on for writing our abstractions. So this starts with understanding a little bit about how Kube itself is designed to be. So this is roughly how we see the Kubernetes machinery. So you have this API server, which is in the center of the universe for Kubernetes. So think of that as a distributed state store, which allows a global view or the global store for all your API objects. So whatever your objects are, be it a pod or any other specs which Kubernetes supports, ends up in this API server. That is what this diagram shows. A user here is actually declaring a spec. A spec is nothing but all the Kube objects are specs. You have a pod spec, you have a replica spec, you have scaling spec. All these specs gets declared on the API server. So API server has a storage, which is a distributed state store, and in the default implementation, it's an etcd backed store. There are a bunch of controllers which are nothing but regular application code which understands basic HTTP primitives. They talk to the API server, and they can actually pull out the objects which the user has represented into the API server. In addition to the regular CRUD operations which a REST APIs normally support, the Kube API server also support an additional one which is called a watch feature. So one of these controllers can let the API server know about its intention of wanting to know about updates to certain events which are happening on the API server, and the API server would push these events or updates back to the controllers. So, and these controllers are also just regular application binaries which you deploy just as regular application in Kube ecosystem. So you can have this complex modeling done and the controllers written all using the Kubernetes framework itself. So to understand how it works, let's look at this picture. So this actually explains how we see an eBay developer goes on with this job of writing an application and getting it deployed onto a Kubernetes cluster. So like everything, like any other project, you obviously start your journey by writing some code into GitHub. So that is the first step here. You create a project in GitHub. And then you go and create a build spec. A build spec encodes the information about which repository you have your code, and where do you want these artifacts to be built and published into. It normally is like a Docker repository or any other repository which holds the binary data for the application. But the build spec is a spec which embodies that information. And you have what is called a build controller, which is constantly watching on the build spec. So a developer comes and he says that, hey, this is like the 4 repos I want my code. These are in the 4 different repos. And I want you to actually build if there is a change in the repo. So it's just nothing like nothing different. It's just Jenkins and others, like, they do the same thing. But we can abstract that idea of building into this build spec, and the controllers can actually spin off like a Jenkins to do the actual job. But for developer, it's just like a single place where he declares this build spec. So the controller, like in this case, the build controller, like if it has the smarts, can actually like kick off another spec, in this case a deployment spec, to take a compiled and build binary and deploy it into the Kubernetes cluster. So the thing which embodies that is a deployment spec. This is a stock Kubernetes object. And obviously, there's a deployment controller which comes as part of the kube machinery, which watches on the deployment objects. Deployment basically says, hey, you have a set of deployed pods, and this is a new version of the containers which I want to deploy on top of that. The deployment controller looks at this information, and it actually like powers, it actually creates like a bunch of replication specs or like other additional objects to deploy your application. So that again is watched by the replication controller, which indeed in turn goes and creates a pod spec, which is watched by the scheduler. The scheduler sees like, there's a new pod which has come up, and these are all objects, by the way. All these specs are just specs in the API server, and all these controllers are watching the API server, and they see additional information getting created. In the case of the pod spec, when the replication controller creates a pod spec, there is no information about the actual node where the pod has to be run. That information is filled in by the scheduler, which is also another controller. So it figures like where it has to be running, and it creates an entry into the pod spec. And finally, like there are the controllers which are running on the nodes, this kubelet and the kubeproxy. They watch on the pod spec, and they realize that they have to be running this particular load, and then they run it. They download the binaries from the repos, the Docker repos, and a pod runs on the node. So this is how Kubernetes deals with specs, and like how you create your own controllers to deal with various scenarios. So we have taken the same approach, and like we are wanting to use the same approach which Kubernetes takes to manage your applications, to manage these clusters themselves. To understand that part a little bit, I have to just tell you like how the things are laid out at eBay from an infrastructure side. So we have a bunch of regions where we operate our data centers in. They are spread, for geographical reasons, like they're spread closer to the customers and stuff like that. And within each regions, you have one or many availability zones. These are fault domain units, where we recommend applications to be in different availability zones for them to be highly available in light of any global failures or like local failures. Sorry. So each of these availability zones are powered by one or many providers. So in our case, we have Openstack, we have legacy, like a bunch of like IaaS primitives which are powering all these availability zones. So our cluster deployment leverages the underlying infrastructure for that. So we have like availability zones, like I mentioned earlier, and in each of these availability zones, we have these network segments which are created for placing the clusters on. So in this example, we are talking about like in one availability zone, it has like two zones. Like we have a prod zone and a dev zone. They are segmented through some kind of SDN or other network segmentation mechanism. Most of the times we use software itself to segment those. So one example to think about that is like if you're in Amazon, this is a VPC construct which you're talking about. So each cluster is in a single VPC. In our case, this is like we predominantly use OpenStack in our cloud. So this will be a set of routers and the network segments which OpenStack exposes. Each of our clusters like have the full set of those things. And at some point in time, like we haven't done it yet, we will have the Federation API server, which connects all these clusters into one single unit. So that is like how we want to go. So to manage all these different things, we have built a component which we fondly call it the TessMaster. So Tess is like the internal code name which we have for our the cluster management solution. And master, obviously, because it's managing a bunch of these clusters all across the globe. So it has a bunch of responsibilities, like and each of them are sufficiently complex in its own merits. And we are going to talk about some of these in the later sessions. So let's talk about, like as an operator, what are the major areas where we have to deal with, starting with networking, which is predominantly one of the complex aspects of like our infrastructure. So the challenges we face in this area are like the following. Like we have multiple networking models. We have a flat layer 3 model, which we predominantly like run our production and the real business critical workloads on. We also have like a variety of overlay based SDN solutions which are there, which runs like not so critical workloads like the dev workloads and other experimentation workloads. We have this legacy data centers, legacy infrastructure. So whatever solution we come up with has to operate and interoperate with that. And we also have this requirement that every single networking layer which we come up with has to share the single global private IP space. So the last one, the global private IP space itself causes some issues for managing the Kubernetes. The first thing is like Kubernetes assumes a CIDR block per node. If you look at the default implementation of Kubernetes, you say, oh, like it has to have a network IP block per host. Well, in our case, we have, as I mentioned earlier, we have like one large IP space for everyone, and then that is not going to work in our case because we easily will run out of the IPs which we have. And Kubernetes is such a flexible framework, we were able to actually abstract out the idea of like IP blocks per host to IP blocks per whatever we are calling an arbitrary network scope. So we created this new object called network scope, and we assign IP addressing to that scopes. And all the nodes in our systems get attached to this network scope. So that is how we have planned this particular problem of not having to have IP blocks per host. We also wrote an IPAM, an IP allocation management system, on top of that. So our IP allocation management system also leverages the kube machinery, and it works somewhat like this. So the cluster administrator creates these network scopes. These network scopes are basically objects which are living in the API server space, just like any other kube objects themselves are. And each of the nodes which you provision into the cluster pools get associated with these network scopes. And our IPAM actually is also another controller, a default Kubernetes controller, which runs in the Kubernetes cluster. What it does is like when a scheduler assigns like a pod to a particular node, our IPAM controller kicks in and figures out like where the node is going to land in, and it allocates an IP based on the allocation pool which is tied to the node. So this helps us like not have any requirements to pre-allocate IP addresses to a particular node. We can have a large pool of IP addresses however we want, and then we can assign the IPs from that block to a particular node of our choice. So that is like the networking challenges, like part, like the quite a bit of like more complexities there. I don't want to go into all the details, but we can talk about after the talk. The other set of challenges we have are the cluster management challenges itself. How do we set up like these clusters? As I mentioned earlier, we have many availability zones, many network zones, many data centers, and we have many clusters we are setting up. So it's a chore to like actually manage all the state across like all these clusters, because as you know, each of these clusters would come up with its own cluster management components. It has its own version of like a software which it has to run. There's a lot of bits which are moving. There are add-ons, there's a configuration state, and on the top of it, you have like the federated state which is coming up. So all these things have to be managed. Obviously, this is a space where a lot of tools exist. You have Chefs, Puppet, Ansible, but none of them gives us the declarative primitives to operate them like Kubernetes does. So we decided to build, as part of our TessMaster, we decided to build an object model, which roughly looks somewhat like this. So we have an object which is called cluster, which represents the needs of a cluster. For example, what is the domain which the cluster exposes? So we numerically name our clusters. So we would have in a cluster number 100. So then the 100 dot, the test.io, that is our internal code name. That will be the name which we would want to create for the clusters. And each clusters would have certain storage class requirements, certain resource capabilities. So all those information about that gets encoded into the cluster. Not just that, it also tells the operator can declare which provider it needs to work with, or what is the region it has to work with. So you specify all these details into the cluster object. And there is a second set of objects which are called compute node pools. So these are, if you would, the flavors in Amazon, or flavors in Openstack, where you say, oh, I need to get bare metal servers which are of this size. It's got 60 cores, or 500 GB of RAM, and there is a set of these nodes which I want to be part of this cluster. There could be multiple such things that are part of a cluster, but you represent them using the compute node pools. And obviously, it has got corresponding aspects of the specification of the machines. They have the placement selectors and other aspects which allows us to get the right machines to add into the cluster. We also have the OS image spec, which determines the operating system which you want to lay down on this thing. So with all those things, this is roughly how the cluster creation flow would look in our scenario. The administrator create a cluster spec. A cluster spec, as I mentioned, is not just one. It's a bunch of those objects which I showed earlier. So they post this cluster spec into a Minikube, which is something which runs locally on your laptop, or it could actually use an existing cluster which is already running. But as you would notice, both of them have the TessMaster controller running in both those places, the orange in that. These are the controllers which are watching for the existence of this cluster specs. So the administrator provisions these specs onto the clusters. Let's assume that it's a Minikube which is locally onto your box. So the controller component gets a hold of the expectation which the user has, and it actually knows which provider to contact because all the information is encoded into the cluster, and it brings up a cluster based on all the spec which it has. And not just that, once it is provisioned, it actually moves the controller over to the new cluster, and it also moves all the specs into the new cluster. And then at that point of time, the controller will start watching the specs which it is managing in the same cluster where it is running. So this is what is called a self-hosting. You host all the components which are required for managing the Kubernetes clusters, be self-hosted along with Kubernetes itself. So that is the, so we just talked about the cluster setup complexities. So after that, the number one complexity for us is the host runtime itself. These are the operating system bits which we are talking about. So as things have progressed over these years, the complexities have been moving more and more into the host which you are dealing with. So now, a host has to deal with a lot of things. For example, the kubelet and the kubeproxy, two interesting things. They both run on the host. You have the networking plugins which are running on the host. We have to manage the keys and other security aspects. We have local storage. We have QoS isolation, logging, monitoring daemons. A ton of stuff happens on the host, and it's managing these host images and stuff are really complex. And also when you think about how frequently we have to upgrade each of those components, it becomes a big effort in itself. So our solution to that is to use a minimalistic OS we use Fedora, Atomic Fedora, but this is roughly how it happens. We have an open OS repo mirror, and we take a snapshot of that so that we can freeze them in time. And out of these frozen time snapshots, we create what are called the OS tree repos. So OS tree repos is a Fedora, Atomic Fedora construct, which allows you to package a operating system binary, and you know exactly like all the packages and their respective versions, and it's like signed image. So you know what is in the image which you are dealing with. What we do, like once we create this image, is also to push it into a container registry. So the entire operating system bits and the repository for that are available as a container. And with this particular image, we actually use the HashiCorp Packer tool to create like a base image for our cloud, which is Openstack. So you start with the known good state of an operating system. You create a binary which is specific to our cloud, and you push that into the Openstack glance. And once the compute nodes, all the new compute nodes which are going to provision will use that particular image for getting as we add more nodes to the cluster, that is what we use. But what about the existing ones? The existing applications, existing operating systems which you have on the cluster will actually talk to the OS tree repo, which is also running as a container in our cluster to get the latest updates. So you just restart them using a deployment construct, and then all of them gets up to the latest state. So that flow goes like that. An administrator goes and create a deployment spec. A deployment spec will in turn goes and creates and changes the node spec. And each node spec has the corresponding node which it is watching. So when you change the operating system on one of those nodes, the node controller does the right things on the back to contact the machine and get it patched up with the latest version of the operating system which we want it to have. Well, in our case, like the operating system has like most of the binaries pre-baked in. For example, Docker is pre-baked in, and most of the bits are already pre-baked into that image. Our policy is like to run pretty much everything into that in that mode, and every components which you want to run on the top of that runs as regular pods, or in rare cases Docker containers. So nothing changes like your host operating system. So in addition to these are like the couple of three areas like networking, the cluster management, and the host operating system management are the three areas where we have defined models for us to operate these clusters. But we also have application modeling challenges. Like eBay application developers are they use a set of known internal models. So when they move to the Kubernetes kind of mode, they also have to deal with the existing internal tools. So we are in the process of writing these internal models to declare the aspects of application. We have a well-understood notion internally of what an application means. So we have encoded all those things as specs. So a user would use the kubectl command and use create application, and you get an application, and he declares what all he wants inside that. And our controllers will go realize that information in all the respective systems within eBay to make sure that it's all good for the user to go. Also, we have internal models. We have a state syncer, which actually is another controller which syncs the state from API server and populates our internal data store for all the operational aspects. We also had to write a lot of admission controller specs. So there is when you operate a site like eBay, there are lots of controls which we have had to put in the past. All those things has to translate down because we are letting users directly deal with Kubernetes. So all those controls, we are using the admission controls. That's a feature which Kubernetes has, where one can write a pluggable solution which allows us to control. Like for example, we will only allow the image if it is scanned for any vulnerabilities, and if it is signed by QA for running in production. So all those kind of situations we handle through admission control specs. So this is another spec which we are currently implementing. So the Ingress spec is like a spec which Kubernetes has. But if you have looked at it, there is a default implementation for GKE. Obviously, we don't have all those things internally. So we implement our own spec using our own internal tools. So OpenStack, if you're using OpenStack, that LB service will be LBAS. So we have a variety of those LB services. We implement Ingress controller to have our own DNS, our own load balancers, and we run all the L7s as regular pods. But an extension of this actually is to do the entire thing. We are planning to get to this model where we don't even need any physical load balancers, but do the whole thing using regular commodity hardware, using Kubernetes, where all the L4 traffic direction and the L7 complexities are all handled as Kubernetes constructs. And if you look at the kube proxy and other things, they are like almost there with some minimal changes. I think we are hoping that we can get to this model where we don't have to have physical hardware, physical load balancers, and other bits in our data center. And yeah, in summary, so for us, like Kube rocks. Like it's one of the awesome pieces of software out there. We can bend and change whatever we need behind the scenes to make it operational in our situation. The good part is like even after all those things, the experience which a developer gets is like pristine. It's the same experience they should get on GCE that they can expect even internally to us. So the API machinery which it provides, it's just pretty awesome. Like you can write your own specs, you can write your own controllers, and you don't even have to use Kubernetes. It does not even have to be Kubernetes. We are using it for many other purposes. So my coworker Sudhi is like going to talk about how we are using the Kube API machinery to build complex policy languages and policy enforcement engines. But that's nothing to do with Kubernetes. Like it can exist outside of Kubernetes. So it's pretty powerful framework in itself. So please check it out. And we are also like seriously considering like open sourcing all the tools which we have built. Like over this next few months, we'll be like actively working on trying to see if we can open source it and see if we can have a set of end users who would love to use the same tools as us, and then go from there. So that's pretty much it. Like, any questions? Yeah. Sorry.
Can you talk about what tools or tooling you use for monitoring Kubernetes and the apps you deploy on top of
So eBay has like a set of like existing large-scale monitoring solution. But for certain small clusters, we also use Prometheus. Something. Yeah.
Is that only for the Kubernetes?
Yeah, only for the Kubernetes layer. Because for the application, like there are like so many other complexities, and scale is like a big issue. So we leverage the existing solutions for that.
Thank you.
I missed what you said. The developers are using directly Kubernetes
Yeah.
interface, or do you have another interface?
So we have an existing interface. So for all the predominant and good flows, like which are the eBay flows, there's a good PaaS layer which we have. So we'll continue to have those kind of layers. But when you have applications which does not fit, like in the keynote, as I said, there are lots of applications which does not fit the paradigm of PaaS. So for those, like we are going to expose like the kubectl command line itself. But not just the standard kubectl, but with souped up with all those additional objects and stuff like that. If you're an operator, you get like all the cluster objects, compute node, pools, and all the other things. If you're an application developer, you get application and other objects which we're writing our own CLIs also. Yeah.
So two questions. How big are these Kubernetes clusters, and how frequently do you launch them?
So the clusters vary from anywhere from 100 physical servers to 200, 300. So our plans are to extend it to like thousands of servers. We are just in the early stages of that. So our typical sizes are like 5K to 10K. That's like size of these clusters which we are looking to get to. But right now it's like 200, 300, something like that.
How many applications would run on a Kubernetes cluster before you launch a different cluster?
So it's not based on, so like each availability zone, we typically love to run a single kube cluster. So our availability zones are like, that's 5 to 10K physical servers. So, if kube scales and everything scales, we would love to have that. And that is that size is determined by like, how much we want to invest in one availability zone. Because more the compute you put, it could run more applications, but the failure domain is going to be bigger. So we have to be judicious about that. Does it answer your question? Yeah, this is a question.
In the example where you were showing that you create this cluster spec essentially, put it in the Kubernetes cluster and then pull it stuff, do you define your own resource object that's called a cluster?
Yeah.
Okay, and then that's
Yeah.
your watch.
Yeah. So if you look at the new project called KOPS from Kubernetes, they also like started doing that. The similar approaches of creating clusters based on a declarative spec. It's no different than the kube pods or anything else, right? You declare a pod and kube realizes the pod for you. In our case, you declare cluster and the node pools, and it actually goes and creates these bits behind the scenes.
How do you map environments to
So right now, like there are like a bunch of clusters. So that is what federation is going to solve, right? You add all these clusters into federation, and you specify like what n you want to run it as a label or some other way, or like you can even we are thinking about writing like the admission controllers like which defaults these values. For example, if you know that cluster is earmarked for one particular purpose, then every object which gets created will automatically get annotated with that value, and then it takes care of it. Eventually, like we want to run all these different environments in a single cluster, but I don't think we are there yet. So there's like a ways to go, but that is the goal. Ultimate goal is to get there.
So the clusters are basically defined once, or we have possibility to scale the cluster, create them when required, and then take them away?
Yeah. So if you delete the cluster object, it just gets deleted. It goes to the decom flow, like but a cluster itself is not significant alone. I mean enough, right? So there are other bits which makes up the cluster. For example, the different type of compute node pools, which makes up the minions. So you could have like let's say a GPU compute node cluster. So another one which is like earmarked for storage. These are all compute node pools. And then you have like a large pool of like general computing cluster pools. So they are all part of like the same cluster, and they can independently be flexed up and flexed out. So for example, I want to like say add another 5 or 50 nodes into that. You change the node pool spec to say that you expect 50 more, and that will drive the backend orchestration to create more compute nodes, run all the softwares which are needed for running the kubelet and other things, and then join it to the cluster.
Do you allow developers to?
No, this is only for operators. Those are operator models, like and it's ABAC protected. So.
Can you shed a little more light on the federated Kubernetes, kind of like the master server that you were talking about?
So federation. So all the Kubernetes clusters come with its own control plane, if you would. So all the etcd and all the master components, they're all each cluster has its own copy of that. But obviously, like if you have tens of clusters, like user would have to know like a lot of details. For example, an application developer says that, run this application in like 3 regions, right? You could actually go and look up all the clusters independently and then go deploy your application in each one of them. Or ideally, you would go to a single place and say, run this application. So that is where the federation is coming in.
So is the idea for example, a deployment, if you want to deploy an application across several clusters, that would go through the federated master?
Right.
Is there some tooling already for?
Oh yeah, federation is a Kubernetes feature. So like with 1.5, it's going to be like almost full-fledged. Yeah. Okay, cool. Looks like there's no more questions. Yeah.
Is your dependency on atomic a hard-coded dependency, or can it work with any other allocated?
The operating system, you mean?
You mentioned OS3.
Yeah. So it's atomic OS. Like right now, there's no hard dependency on any of those things. So that you can write a new controller which understand different operating systems, upgrade procedures. The specs does not change that much. It's just like how. So that's the beauty of it, right? The spec, if you are designing it properly, like then you don't have. The only thing you are changing are the controllers themselves, not the spec. So you can. Yeah, Kisan.
Yeah, just curious. What networking layer do you actually use in your
So we have like a SDN solution which we use internally, and then we typically tend to favor the flat layer 3 networking. So.
And how do you manage namespace between developers?
So namespace, so we auto create namespace. So when you log in, based on your credentials, the authorization token which you have, we figure out your association to some groups, and you create namespaces automatically for you. You can also create your own as many number of namespaces here. So, yeah.
You had different clusters for pod and different clusters for development and for production. There are other approaches I've seen is using labels. Is there pros and cons for you?
Well, it's a maturity curve, right? So we need to be comfortable at some point in time to run both. Because you don't want the developer taking up all the space, and preemption and other things are not yet there. So once the preemption and other features are there, we would want to run everything in one single cluster. That's the goal. Cool. Thank you.